There's no better way to start on these related rates than just to get into it. We're going to be playing with the chain rule. I don't know whether you've noticed, but there's two du's there that could sort of cancel. And if they cancelled, what we'd be left with is a dy on a dx, which is the same as the other side. So algebraically, that's sort of cool, isn't it? That's the pattern we're going to be looking for here. And once you see what we're doing, it's a little bit fun. An oil slick is expanding such that the radius... So the radius is actually changing in size over time. So it's changing at 0.5 metres per second. So the radius is changing in a distance with respect to time. So it's dr dt. And we're wanting to find the rate the area is going up. So that would be dA dt. And that's got a big question mark. So we're going to play with these two things there and simply go dA dt. We're going to come back here and go, see this dx? It's on the bottom in that second term there. So when we see that dA dt, we know there's a dt back there. Well, that's what that thing is. So that's a dr. So because that's a dr, we need to cancel out that dr. And the thing that's missing on the top is that dA. So if they were to cancel, we've got the dA's on top and the dt's on bottom, and we're all good. But we're missing what is dA dr. Well, we're talking about a circle, the area of a circle. Oh my gosh, there's an A and there's an R. So I can differentiate to be 2 pi r. So now I know that my dA dt is dA dr, which is now 2 pi r times dr dt, which is this thing over here, times a half. So we're going to use that and go, when the radius is 20, when the radius is 20, there we go. So that will be 20 pi. And we're talking about an area, so that's metres squared per second. That's how fast the area is changing when the radius is 20. You'd understand that a really big radius means that I've got a big circle that's changing quite quickly, and a small radius, it's a small circle, so there's not much difference to the area. So that sort of makes sense. The R has an impact on how quickly the area is changing. Okay, next one. A balloon is deflating. A balloon is deflating. And we want to find the rate that radius is decreasing. So that's dr dt is we don't know. Air is coming out. Air is volume. So we've got a dV dt is -6. And what are we finding? That's right, dr dt. Okay, so let's just go. dV dt. So we need the dt at the bottom. So that's that one, yeah? dr. So that means we need a dr at the bottom and a dv at the top. That's what we don't know. We've got to generate that volume of a sphere. So now we can do our dV dr. So we get this thing here is now dV dt equals 4 pi r squared times dr dt. Now, you will find the textbook will probably want to put that as the subject over here and then do all sorts of flippies. But I'm saying it doesn't matter. That just comes to you, doesn't it? That's easy to look at. It's easy on the eye. So that's okay. Here in the question, we know our dv dt is minus 6. So I'm just going to put my minus 6 here. My dr dt is my unknown, so that's okay. 4 times pi times... Now the question said when the radius is 6, so that would be 6 squared. And I just want to get dr dt. So let's go minus... Those 6's will cancel, so it will be 1 on... One of those 6's, 4 6's are 24 pi. And it's a volume, so it'll be centimetres cubed per second. It's not a centimetres cubed, it's a radius, so it's just centimetres per second. That's how quickly the radius is changing. Clearly it's getting smaller because it's deflating. How much fun is this? I should show you that all on one page. There you go. Okay. It's a little bit haphazard, but it comes down to playing with this chain rule. Let's see if we can knock this last one over. Okay, the ladder is being pushed up against a wall, so here's the ladder. There's the wall. The ladder's 5. We don't really know this distance. So let's make that x, and let's make that distance y. So we're pushing the ladder up, so it's, getting taller and taller on that wall as I'm pushing that way in. Hopefully we've all been on a ladder. Excellent. Just rub my diagram out. Here we go. Okay. So, we are getting dx dt, so we're being pushing towards the wall. So the dx is getting smaller at a rate of 0.3. So I guess that's minus because it was getting smaller. We want to find how quickly it's going up the wall. So that would be dy dt is what we want to find. So let's see if we can find out what we're going to do here. Dy dt. I've got a dt, which is a dx. And that dx has to be on the bottom, and then a dy is missing on the top, so that when we cancel, we've got this dy dt. Okay, so there's our pattern. What's missing? So I need to find the relationship between x and y, and I reckon that's a right angled triangle. So what's 5 squared? 25. So there's my relationship between x and y. 2x plus 0 minus x on y. So we're good at that implicit differentiation now, aren't we? So there's our dy dx. So I can go dy dt is what we want to find, is minus x on y times dx dt. And we are given dx dt. So that will be times, come on, get out of there, minus 0.3. Now the question says, how fast is the ladder moving up the wall when the lower end is when x equals 3, yeah? So we're going to set x equals 3. Now, if x equals 3, then y equals 4, because it's at the 3, 4 triangle. You just got to have x and y because that's required in dy dx. Okay, so dy dt is minus 3 on 4, because that's what we had before. X was 3, y was 4, times minus 0.3. Minus 3 times 0.225. Everything's in, that's in meters per second. This is meters and that's meters, so that must be meters per second. And it's positive, therefore my y is getting bigger, which makes sense. It's going up the wall. Okay, that'll do. Jump in, do some practice. We'll do some harder ones in the next video.